Okay, thank you, Sarah. We're going to talk about building energy basics. And that's part of the overall program here of assessing your performance. Remember last week or last month, rather, we talked about the process of developing a team and what the team is going to do, right? And one of the first steps, or the first step, is the commitment. You've made the commitment, you're back here again. And then after that, we want to talk about assessing what the current performance really is. That's one of the next steps. And in order to do that, we wanted to give just a little sort of simple, without getting too technical, explanation of how the energy systems in a building work and what kinds of things you should be looking for. The purpose of operating and maintaining a building in the so-called built environment is to provide fundamentally these three things. First, it has to be healthy, safe, right? And so in operations and maintenance of a building, you're going to have various things that support that. You're going to have ventilation. You're going to have heating and cooling that's going to keep down the amount of mold and mildew. You want the building, secondly, to be comfortable. You don't want it too hot or too cold, which is the number one complaints, by the way. It's hot, it's too hot, it's too cold, it's too stuffy. And lastly, you want to have this environment induce productivity to the building occupants. However, all these things require energy. In fact, to provide any of these requires a lot of energy, and it's pretty expensive, getting more expensive. It's also causing a warming problem. It seems like only yesterday they had another example of the snow crabs up in Alaska. Did anybody see that? The temperature of the water in the Bering Straits come up 2 degrees, and they've gone from 9 billion to 1 or 2 billion, some small number, in over since 2019, over a 3-year period. Pretty scary. But this is how buildings use energy, and also the portion of energy. This is a national thing, by the way. It's different than what we see in New Jersey. It's different in an urban environment. I would consider Trenton, where most of you are, is an urban environment. As an example, here it says buildings consume roughly 40% of the energy on a national level on average. However, in New York City, we know that it's about 70%. And I'm going to say Trenton's probably 50, just a guess, but and then it gives you a little insight. They differentiate between residential and commercial buildings, and they use energy similarly, but somewhat differently. The biggest differences, I guess you would see, in most commercial buildings, you don't have as much refrigeration, so it probably uses about half as much as it does at home. Cooling, 10% at home. In a commercial office building, about 13%. The heating in a commercial building, again, these are national averages. Heating 16%, whereas at home it's twice that. Probably because of the larger envelope in a commercial building. Although in order to ventilate and heat and cool a large structure, although there's some geometric efficiencies, this also means you've got to move the air in and out of a whole lot of places, and that takes a lot of fan horsepower and electrical expense. Ventilation, 7%. That's, if you look at what it takes to cool the building, 13%, and then you look at ventilation costs about half of what it costs to cool the building. Now, why is that? Well, because you got to take all that cold air that you made and you got to throw it out. Fortunately, there are technical solutions that'll help with things like that. You can have, you'll see today an example of an air-to-air heat exchanger that recuperates some of this ventilation air that you have to throw out. But this gives you a rough idea of what we're dealing with. And I would say that in most of your buildings, you're probably on, rather than 18%, it's a larger portion. But these are portions of a national energy demand. And when I say demand, what's the demand? Well, there's electrical demand, and there's also thermal demands. And these are also paired or reflect the load. What is the load? What do we mean by that? Well, it really refers to the amount of energy that you're using at any given point in time. So it is time dependent, the load profile. It goes up and down pretty much every day in the building. Usually the weekdays are a little different than the weekends. And then there's seasonal things. The loads go up and down. In the summer, your electrical load should go up and the cooling load should go up. But the heating load should go down. And this gives you an example here of some, when we say energy and thermal loads, we're talking about a total energy here. So they're both thermal and there's an electrical component too. But from these loads, they come from various places and they have internal loads and external loads. The external loads are things that affect how much sun or heat from the outside or moisture from the outside comes into the building, how much air infiltration you get. Those are considered external loads. And internal loads, all this lighting we have puts off, besides light, what else? A lot of heat. So, and that heat doesn't go anywhere but in here, right? So if you're putting it in here and it's a hot day, now you have to remove it. So it makes sense to have lighting in the whole building approach that will lower, not only provide you a lighting for less, but also reduce the cooling load. So the whole concept of load is a little difficult to grasp, but realizing that some of it is internal, some of it is external, and more importantly, what is it that we can do to reduce the loads? So in a program to reduce greenhouse gas emissions, which is one of the big purposes we're all here, we have to talk about first reducing loads before we decide we're going to put in a cogen plant or put in PVs or whatever. What we want to do is reduce the loads, do the things that will lower the amount or the requirement for electricity or fuel before we do other things that will, particularly something like on-site generation. You want to be able to reduce how do we reduce loads? Well, we can put insulation on the building, right? We can caulk. It doesn't sound very exciting and insulate, but insulating the pipes and insulating the building itself and doing the caulking and getting all these holes that are inevitably there sealed up can save a lot of energy. Regulating ventilation appropriately can save a tremendous amount of, I've seen situations where we were doing air changes, 12 or 13 air changes per hour on a 24/7 basis, if you can imagine. This is in a 500,000 square foot building. So what that means is if it's 12 air changes an hour, that literally means every 5 minutes, you're opening up every window in the whole place and you're blowing all the cold air out of the building or hot air out of the building and then making up for it again. It was a complete energy hog. So what do you do in a case like that? Well, you look and see, why did the engineers have this high ventilation rate to begin with? Well, there were fume hoods in the building. Okay. So now you want to get Phoenix controls to get your fume hood so that when the sash is in a certain position, it lowers the ventilation rate. You get occupancy sensors, you get CO2 monitors, you get all these different wonderful technologies we now have to reduce the demand. And we did talk, now people are, you don't think about it so much, but people actually do create a cooling load in the summer in particular. In the winter, I think it's offset a bit. You don't have to heat as much. So it can be good and bad. And you can see these external loads here from the sun, from just the air being cold and coming in from the ventilation infiltration coming from the outside. In addition to the lighting that we talked about, all these computers we have, and over in the computing places, there's a lot of heat that you have to get rid of one way or another. And you'll see when we get to the energy audit later today, a situation where, you know, they have excess heat, but they have, in some cases, they turn the central system off and they have a local Liebherr unit or something that'll provide heating and cooling for computers. And as I said, every month, really the monthly loads vary, but what you'll see with monthly loads, when you begin to look at the information, and Sarah talked about, well, we need to have the information. We need to know what your utility bills are. We need to know what your spends are. We need to know what your thermal and electrical loads are. So the three things you should know is how much money do we spend on that building every year? Just first, for starters, figure out for 1 year, what does it cost? Secondly, how many square feet does that cost, is that cost associated with, right? And then the third thing is what's the breakdown between electric and fuel? And then you look at it on a monthly basis and break it down that way. And now you're just using more or less common sense. I group the monthly things together. I have summer, 3 months. I have the 3 months of winter. And then you really have 6 months of what you call shoulder months. That's where it's not real hot and it's not real cold. Yeah, you get some hot days and cold days, but by and large, if you look, once you get past, you know, the beginning of March or so, things usually let up a little bit, right? And it starts to get a little more moderate. Even now, a day like today, I mean, my heater came on last night. I really didn't need too much, but it was 32 outside. But typically, if you look at last weekend as an example, it was beautiful, right? You shouldn't be running your air conditioning. You shouldn't be running your heater. And when you look around, you will find they're running a lot more than you ever thought they were. And then you want to look at those things. You want to look at particularly first the shoulder months and ask yourself, are we using more or less, do you use more or less fuel in the summer than the winter? In the fall and the spring, are you heating less and cooling less? And if you're not, there's something running all the time. When I got off the turnpike this morning, the very nice woman in the toll booth, and I said, "Oh, how are you?" You know, she said, "Oh, hi, how are you? Great day." I said, "Good, good." I said, "How's everything with you?" She said, "Well, I'm cold." I said, "You're cold?" She said, "Yeah." She said, I said, "Well, don't they have a heater or something for you?" She said, "Well, I have an electric heater in here." Oh, that's great. I have an electric heater in here. She says, "But the air conditioning's on and I can't get them to shut it off." I said, "Well, can't you block it up?" She says, "Nope." She said, "We've tried, we can't block it up." I said, "Well, are your feet cold?" She says, "Oh my God." Anyway.
Who was honking behind?
Yeah, no, fortunately, there was nobody behind me, but you know, after all that, I forgot to get my receipt. So Vicki remembered that. I didn't get my receipt for that. Lighting, plug loads and equipment. These collectively actually amount to a lot. And we're going to start looking at basically and when we switch from that into here, we're going to talk about where are the lighting, where are the plug loads on here? So in classroom, food, office. Okay, lighting, plug loads, here we are. You see the plug loads, the second to the last column on the right? those are given, and actually look at just the second column from the right-hand side. That's in watts per square foot. You know, most of us don't think about watts per cubic meter, but watts per square foot. Look at a classroom, 0.9. I guess this is probably, that's a lot for a classroom to have a plug load, because this is almost like a typical classroom, right? But we have plug loads up here, computers. Not in this room, we don't have a lot. I guess if we had coffee pots and all those kinds of things, we would. Food service, well, food service isn't too much more than a classroom. I don't know why. Office, look, that goes up to 2.5 watts per square foot. So some of these metrics, not only watts per square foot for the various different kinds of load, these are different kinds of load, right? The plug loads are one time, and then lighting is identified here as another. Now, when they say equipment, I'm not sure. This came from the DOE, right? I mean, from EPA. Yeah, it came from
DOE.
from DOE. Yeah.
Your infrastructure.
Well, I think so, but
Your water heaters.
I think it's HVAC too, but it doesn't look really high enough to me. But I guess that's about right. I guess it's per square foot. It works out. So yeah. So those are the big three, I guess, really, right? Lighting, the HVAC, and then plug loads. So we're going to take a poll now. Did everybody have their little thing, their scanner thing? And we're going to ask this question here to optimize energy use. What's the correct order for implementing the following energy efficiency activities? So the first choice they give, I guess you're supposed to put these in order, right, Vicki or Dean? And
They're in order and you just pick which one.
oh. 17% of you said it was number one. Another 17% said number two. And then a whopping 67 or 2/3 said number three. Who answered number three that you remember? Do you know why you used three?
I just figured if the double will show its speed to reduce it to make you have less people, in the office, if you have, less computers plugged in, less plug loads on.
Right. So before we put in a PV system, before we put in a cogen, before we do some of the more exotic energy efficient or energy producing type of project, we want to look at the simple things first, right? We want to insulate the roof. We talked about this a minute ago, right? And do some of those, and then anyway, we can move on. But three really is the correct order. I can understand the use of efficient systems and controls. Some of that, for instance, efficient system, if it's lighting. I would say lighting, you could go ahead and do that pretty much. You shouldn't do it in a vacuum, though. It should be viewed with the whole building, what we call the whole building approach, where you kind of look at the building and the site-specific things that are associated with that building. And then it looks, lighting in most cases, if you do it in a certain way, it's almost a no-brainer, but it's not easy to do it well. There's all kinds of choices in lighting projects, and we'll talk a little bit about that further on. But let me go ahead and click us to the next slide here. So here we are with the big three, and this kind of shows where these loads are located in your building. So for space cooling alone, it looks like about 1/3 of the energy that's consumed in the building And again, these are national numbers, but I think this is probably fairly typical of our area of the country to use about a third of the energy strictly for air conditioning. Lighting 27% is probably an old number for New Jersey because we've had a couple of big iterations of lighting upgrades. So I'm thinking in New Jersey rather than 27. It used to be, 25, 27 used to be a rule of thumb number, but that was 15, 20 years ago. Today, I think it's probably somewhere in the high teens on average here. Ventilation, they're only showing 3%. But now we showed on the national level before in a commercial building, it was more like 9 or 7. Yeah. So what are some of the things we can do to reduce demand? Well, like I said, we improved the building envelope. Doesn't sound too exciting, but it's more than just insulation and ceiling. Windows are very important. Any type of doors or windows, particularly those that are subject to solar gain, can have a huge impact on energy consumption. The solar gain helps you in the winter. It hurts you in the summer. You can install things like window shades that can help do that without doing anything else. Although you can't do that in a vacuum, you got to consider daylight, right? And then regular behavioral best practices are, I think in our first meeting, we talked about that, and we did a poll or we did a talk, and everybody, or I guess a group discussion, and a lot of the groups had the same theme, right? And it may have been Tom or somebody that was talking about reducing demand through one of the least expensive ways, the so-called low-hanging fruit, is to try to change the habits of the building occupants. And one of the best ways to do that is really, you have to have some sort of communication plan. We talked about that last week, but also you have to be able to tell your story. And if you tell your story to the building occupants, what's your track record? What are you doing? Where are you going with your energy management program? And show them some basic real figures. I mean, you have to know how much you're using every year and every month for electricity and fuel, but then you can pass that word along, and it can change behaviors. Adding insulation is pretty straightforward, not always simple. I mean, what do you do if you already have a solar array on the roof? Well, I guess maybe you can put it in from underneath. High performance windows. In some places, those are really clutch. They're expensive. But I've worked on some skyscrapers in New York where triple pane, as expensive as they were, it was a long payout. But it was still within a 10 or 12 year payback. Now for state facilities, I had a boss, he said to me once, we were talking about payback and putting together these energy projects. And he said, you can go up to 12 or 13 years. I said, really? I had come from the private sector and we were used to 3 to 5. I mean, it was just, we're not going to spend money on anything we can't get it back in 3 or 5 years. He said 13. I said, oh, okay, well, let me think about that. And I really, the cogen was good. It paid back in probably 7 years. But now it's been running 25 years, the same plant, The lighting, some of the stuff paid off in a couple of years. And, it could have lasted 20 years or 30 years, but there were new innovations in lighting. We did replacements maybe every 12 or 15 years. Reducing infiltration, that's a lot more than you think. It's subtle. Has anybody ever had a blower door test done in their building? What did it tell you?
They couldn't even do it. They didn't bring enough blowers.
Because it was, there were so many holes. Oh, my. Yeah, amazing, right? Yeah. So here's kind of a little bit of a schematic, if you will, of how energy, heat moves throughout buildings. They have wind pressure. That when you get wind, that increases the amount of infiltration, right? On the windward side, anyway. Stack effect is, you know, in these tall buildings, that's a lot more energy and a lot more force, I guess you would call it, right? The stack effect is really, it's a force that moves air upward. And having a certain amount of elevation, even how many stories on this building? Maybe 10 or 12? Is it that big? It's a fair sized building. Most of you are in buildings that are, you said yours, Christopher, was 12, 13. A lot of you are in tall buildings, and it creates this buoyancy of the air that moves air from way down in the basement all the way up to the top, and in some cases out the roof. Elevator shafts, oh, that's a good one. You know, if you go up, if you go to a typical elevator room up on the roof, half the time the door's open. Half the time the door's open. Particularly if it's hot, you know, those rooms get hot, and for whatever reason, they have to put fans and everything. Okay, well, anyway, that's sort of self-explanatory. Bathroom ventilation in New York City is a very big deal. They have all kinds of standards and regulations you have to follow, and they throw out a tremendous amount of air. And then just regular breaches in the basic envelope. Air moving and leaking between common areas and other partitioned off areas. And then there's just the general airflow in and out. Daylight harvesting. This is a great one, really. And buildings where you have natural light coming in. Look at these lights are on. Look how much light's coming in. It's a natural, right? It's not that difficult. Now, in some buildings, it could be like Kimberly's in some of her buildings, and other buildings, I think maybe Christian's building, or Christopher, not, you know, it was Christian's building. He said some of the walls are so thick that you can't really use the Wi-Fi for controls. The Wi-Fi controls are really terrific. But now if you're just controlling a room that's next to a window, and maybe you could just have some sort of local network. You don't want to really be rewiring things if you can avoid it in an older building. But I think you could have a local router or something and avoid the problem of having to rewire something. But for daylighting, let's pretend this building has windows along this wall. You're going to see in the exercise later today where we have a lighting retrofit with LED lights, and then we have occupancy sensors, and we have daylighting. And to do the daylighting, if this is a window, a wall full of windows, and you have these 2x4 fluorescent or LED light fixtures, luminaires, all you need to control that is some sort of light sensor that's located over in this area that will sense the amount of daylight that's coming in, that will send a signal to a dimmer, and it'll dim. Maybe these circuits are separate. You probably have to separate those. But you could dim that circuit so that you would, if it was summertime, what would you be doing automatically when you dim that? Besides the energy you're going to save from less light,
Reducing the heat load.
You're gonna reduce the heat load too.
Or LEDs, that's not like.
Well, it's less all the time. It is less all the time, but it's on a relative basis, it's still a fair amount. Even though LEDs are highly, quote, efficient, the efficiency really, and you'll see later when we talk about lighting this afternoon, right? The efficacy is the number you want to look at, the amount of usable light that you get. They don't give off as, when you have less usable light, where do you think the extra energy that was going, that went into heat, right? So it's still going, a fair amount is still going into heat, even though it's much more efficient and efficacious. It's still, there's still a lot to be had, I guess. So yeah, this kind of shows how it works. And then we talked about the behavior. And then now Energy Star really gives you some really good ideas. And Dean really found a lot of this stuff just right off the web, right? But it's very good material. And I'd encourage anybody to look at some of this stuff. We gave you some last week. If you didn't get it, we'll make sure you get a copy. Did you bring any stuff from last week with you or no?
I didn't bring any, but we're going to be putting
You
them
can
all up
send
on the
it.
website and they'll be able to access them
There you go.
on the
Yeah.
website, yeah.
Okay. So then, look, yeah, after we've reduced the demand, then what do you want to do? Well, you want to continue to use efficient systems, you know, get a good coffee pot that doesn't use a lot of juice. And then it says mostly at the end of useful life. I think there's that is true in a lot of cases. But sometimes you can save a lot by replacing it early too. Controls, we talked now, does this show internet? Well, yeah, you see how they had cybersecurity on there? Artificial intelligence, and that's a new one, relatively speaking, but a profound one. And I think I mentioned it last week. What artificial intelligence does is it machine learns, and you can set up your building automation system or your energy management system within the building to learn the behavior of the individual groups of equipment in your building, HVAC equipment primarily. But you can also get down to the plug load level and the controls on plug loads. Somebody was asking, I think it was Mike, if we had a vending machine in the building. But at Rutgers, we had 6,000 Coke machines or something, a lot of vending machines. And somebody got contacted on my staff about an energy savings device that worked with vending machines. I think they called it Vending Miser or some such thing. And I was kind of skeptical about it, frankly, but we got two of them to start. We put them on the machine. We got little watt meters, and you plug it into the watt meter, and then you plug the watt meter into the wall, and it tells you how much your vending machine is using. So we did this for a few months, and we said, son of a gun, it was saving a lot of energy. We were surprised. Somehow it sensed, I don't know, have an occupancy sensor or something when somebody was standing in front of the machine. And I guess at night, it lowered the temperature or turned off the compressor, did something. All I know is we never got any complaints about the soda being too warm. And it saved about half of what we were spending before. And so it was, and I think I asked the other day, I said, are you still using it? I said, oh yeah, we still use it. That was probably 20 years ago. So it adds up over time. And renewables now, unfortunately, cogen is not considered a renewable, and rightly so. In many cases, though, it can be an application to help get us into the transition where we can get to net zero. And the only way of really getting to net zero, Public Service told me 15 years ago, 20 years ago, that their company was going to focus on solar energy. They felt that solar energy was probably the best. Conventional things, people say, oh, well, you need all kinds of stuff. You need wind and you need solar and you need hydro. And yeah, well, yeah. But to get the amount of electricity that we need, I kind of agree with public service that the PVs, if you just have them everywhere. And when you go out to Arizona, they have them everywhere. You go into the 7-Eleven, they got them in the parking lot. You go to the hospital, they're all over the place. You go to almost any school, anywhere around Tucson or any of those types of places, lots of photovoltaics. You don't see a lot of windmills. You see them out like in California. And I guess we in New Jersey, we built offshore wind, pretty large facility. In Maine, a friend of mine came up to visit me there this summer, and he looked there and he said, I don't see many farm animals around anymore. He said, what's going on here? I said, yeah, no, there's still farm animals. I drove into town the next day, looked around, there wasn't a single farm animal out there. Everybody's now gonna lease their land to NextEra or somebody to make solar power. And the farmers are doing that now instead up there. So wind, in various locations, people complain about the noise sometimes. I guess in Palm Springs and stuff, maybe it's not so bad. It's kind of desert and it's not bouncing off of much, maybe. Biomass, it's renewable. I think it's still got CO2 trouble. Hydro is great, but we just don't have enough of it. Solar hot water has an application. Photovoltaics are always good. Somebody was talking about their roof and the condition of the roof. Land mounted one. We did a 4 megawatt land mounted project over in Piscataway. Actually, it's in Edison, and it's been doing real well. Yeah, sure.
You guys are going to do solar, you have to do it through the same contract, there's a size limit. How do I talk to the fee? He gets his work out of the solar at this site,
Okay.
and you have to go through the state contract. GFC project. I don't think it'll be bigger than 5 months.
Well, 5 megawatts is a lot, right?
The advantage is you don't have to have anybody maintain it. Though.
Yeah, it's gonna be total PPA.
Uh-huh.
And I think Christian, we tried to build some good, but
Well,
the beats is the furthest along, so.
Yeah, we tried, but unfortunately our district.
But the power purchase agreement works, right? Nothing wrong with it, really. These I'm not wild about, however, the fuel cell. I don't know, we had them, Ramapo had a couple. Last time I visited the campus there, they had gotten rid of them. We went in to see one, they put one in the NASDAQ building in Manhattan. And they were so proud of it. And we, the energy engineers all got together and we went to look at it. It was cool. And this training facility that I work in Chelsea, one of my fellow instructors works in that building. He's a chiller operator and he teaches chiller operations at the school. And I said, well, how's that fuel cell doing? He goes, we don't have it anymore. So, okay. So now the cogen plants are all still, well, I take that back. Camden, they ripped out for some stupid reason, but Rutgers, New Brunswick, in Piscataway still has, in fact, we've repowered that one. Newark campus still has they're going strong. They're about almost 30 years old now. Okay, so this is the whole building approach, really kind of putting it all together. And these are just sort of show some of the technologies, high efficiency lighting, electric vehicles. A lot of you talked about putting in the infrastructure in your site, right, to handle electric vehicles. Heat pump hot water that one's really gaining a lot of popularity, as are the mini splits. When I walked in here last month when I came, I saw a couple of HVAC service people out in the building next door. And I said, what are you working on and stuff? He goes, oh, we're putting in a mini split. I said, really? You putting a lot of these? He says, oh, yeah, putting in lots of these. Okay, so that's it, just a little bit over for break. Any questions?
Talk much about geothermal.
Geothermal, I'm glad you brought that up. Geothermal is a very good one too. And we put that in two different locations that I'm familiar with. The one was over where Lynn Stiles was. Is that Stockton? That's right. Stockton had it, and you could probably get a lot of good information there. They also put one in right across from the power plant that I was in Newark. At that high school, they have a special high school there, and they put in a geothermal there. But geothermal is a great idea, and there's some applications where it's just a natural. But basically, the way geothermal works is it is a heat pump, and it takes the heat that's in the ground, and it essentially boosts that, and I guess you could think of, but it transfers that heat, even though it's low grade heat, because it's a lower temperature at 45 degrees, let's say. You can take that 45 degrees and you can actually extract a lot of heat out of the earth. And then you take that heat and you use it to heat the building or cool the building, because you can reject that heat into the ground as opposed to rejecting it in the air, particularly avoid the problem of having a cooling tower, which has its own set of issues, right? Good question, though. And I would say in the right application, if you have the real estate to put it in, and you can put in a field of some sort that makes sense. I think, I know where else they did it. They did it at that STEM building over at Kane. Anybody go to Kane here? At Kane and Union, on the Union campus, they built this special mathematics building. And they have 3 large heat pumps in the heat field outside, and it's another good one to look at. They've done some in the past. I know they did a couple of dormitories years ago, and I think they did a couple of dormitories at college in New Jersey. This is a campus way. Okay, well, I have to catch up with them. Ted Boer there. Do you know him in the central plant?
I do not.
Okay.
I just looked at the website, I found it.
Yeah, that sounds good. Well, maybe we should have a plant visit over there with the class. It would be good. They have a lot of good things at Princeton. I have a lot of respect for them. They have thermal storage. They have cooling. They have some of these geothermals. Years ago, they took me through some places and showed me where they had these heat wheels, and then they had desiccant dryers. They also use the AI that I referred to. They use a proprietary brand called PackRat, but basically it goes into their building automation system. It learns how they work under certain circumstances. Then it learns that, okay, this is the way when they're optimally adjusted, that they work. And then if they don't, they give them a signal. They call it FID, FDD, fault diagnostics and detection and diagnostics, right? So, okay, good question. Anything else?
Just in terms of what Paul was saying about heat pumps, it is something worth tracking. They seem to have moved, heat pumps stock being really valuable, like down in Maryland and places like that, because as you move north, they weren't efficient in temperatures to drop below a certain 40 degrees or something like that outside. So up here, they wouldn't provide heating in the wintertime because they couldn't deal with the cold. Combination of climate change, but also the technologies have gotten way better. And now they are efficient up here. They can go down to much lower temperatures and provide heat without kicking in a radiant oil, which was then, diminishing their overall returns in terms of energy. So it's just definitely a technology to watch. It seems to be just like lighting. It seems to be on the move in a way that wasn't anticipated even 10 years ago.
Yeah, that's absolutely correct. Yeah, They've gone to these seasonal adjusted energy ratio numbers from, say, 10 up to what, the high teens now, I think. Almost doubled the efficiency of them.